everybody. Good morning, good afternoon, good evening, whichever is applicable. My name is Mark Brown. I'm the National Sales Manager for Techimp, and we're going to discuss condition assessment of medium and high voltage cable systems today, specifically through online non-destructive partial discharge testing. Before we start, I'd like to briefly review who we are. We're part of Altanova Group, which basically consists of three companies. ESA, who's been around for 80 years, and they manufacture portable test equipment, circuit breaker testing equipment, tan delta, and such. And then there's Techimp, which is what we're going to be talking about today, who specifically is a global leader in both partial discharge testing and monitoring solutions of all electrical assets, not just cable. And then Intellisol, who's also a leader in medium and low voltage monitoring for temperature, humidity, and also partial discharge in medium voltage equipment up to 40 kV. All right, so we're the Altanova Group, made up of three companies. We're a global company in condition-based monitoring and diagnostic of all electrical assets. All right, so that's who we are. Who is Techimp? Well, again, we do partial discharge testing and monitoring of all assets, including power transformers, of course, cable, gas insulated switchgear, medium voltage switchgear, motors, and generators. So pretty much all assets, both testing and monitoring. Again, we're a global leader in partial discharge. Everything that we manufacture, we design, engineer, and build in-house, including our sensors and software, which our software is patented, and our sensors are proprietary. We were headquartered in Bologna, Italy, and we also have a headquarters here in the U.S. out of Alpharetta, Georgia. We also have headquarters in Germany as well, and other locations. All right, so let's talk about why partial discharge is important. I think we all know reliability is important, so we don't need to discuss how important reliability is. So what's the challenge out there? Well, of course, the challenge is that assets age. And as they age or approach the end of life, insulation breaks down, and that's where partial discharge comes in. It helps you understand the health of the insulation, and therefore the health of your electrical assets. Helps you determine what needs to be replaced or repaired, and also sometimes more importantly, what doesn't need to be replaced or repaired. Let's talk about testing for just a minute. The first two tests you see there, factory acceptance test and commissioning test, are done online. They're done offline. Obviously, the first one is done at the factory, and then the commissioning test is done in the field. But both of these tests are offline testing for new cable. And the way it's performed is it's connected to a power supply, either a VLF or a resonant test set, and then a voltage is applied. Usually starts about 0.5 UNOT or 0.5 rated voltage, and then the voltage will be stepped up all the way up to either 1.5, 1.7, or sometimes 2.2 UNOT. And they're looking for any types of defect in the cable before they switch it in. Okay, so it's an offline test where an overvoltage is applied to look for any defects in the cable. What we're going to talk about today is different type of testing. It's online non-destructive testing, and it's for assets out there whose insulation is aged or cable that's aged. And we do it online because the last thing you want to do is put an overvoltage on an aged cable. All right, so it's done online at system voltage, no switching out. All right, if you overvoltage an aged cable, the very least you can do is shorten the life of the cable. or at most, you could blow up the cable. So this procedure is done online at system voltage, and there's no switching. All right, so before we proceed any further, if you have any questions, feel free to type them in, and we can address those as well. Feel free, and if you want to, you can ask it live as well, anytime. All right, so let's start with what is partial discharge. I think a lot of you already know what partial discharge is, but let's just review it real quick. Basic understanding of partial discharge is nothing more than a spark or an arc that happens inside the insulation of an asset, whether it's cable would be internal or tracking or corona discharge. And it happens in either flaws, cracks of the insulation, microvoids in the insulation, and also in water trees. Water trees are basically microvoids in a cable that's been energized for a period of time with the current flowing through it. Water trees will develop in the cable, and how it happens is water diffuses in the insulation. It causes these water trees. And water trees aren't inherently dangerous to an insulation, although it is a degradation of the insulation, but it won't fail the cable. What happens is once partial discharge happens inside these water trees or these microvoids, the insulation will fail. All right. So that's what we are measuring for, is partial discharge in the insulation, in these microvoids or cracks or flaws in the insulation. All right. So we're measuring for partial discharge, and through amplitude and repetition rate, or more plainly, how many times it's happening per cycle, we can determine if that partial discharge is dangerous to that asset. With that being said, you should be asking yourself what we're actually measuring. So our equipment goes in and measures the partial discharge. The answer is that when partial discharge happens, it emits RF signals. And through the amplitude and frequency of these RF signals, we can determine the danger of that partial discharge. So the key here is when we go in to measure partial discharge, we're measuring RF signals. Okay, National Fire Prevention Association is an association in the U.S. Has stated that the #1 cause of electrical failures is insulation breakdown. Okay, so the #1 cause of failure is insulation breakdown. And the best test for insulation is partial discharge. Partial discharge is the best tool to evaluate the health of that insulation. I get this question a lot. What's the difference between partial discharge and infrared? Or actually, more so, I get the question: does partial discharge replace infrared testing? And the answer is no, it does not. They're two completely different tests. Infrared testing is more of a resistance test, a heat test for high resistance. And partial discharge, again, is a insulation test. All right, IR cannot detect insulation breakdown. So both tests very important, but two completely different tests. And most people will test for infrared, but they're not testing for partial discharge, and it's a very important test. All right. So let's talk about partial discharge testing methodology. First, we acquire the PD in ultra-wide bandwidth mode. What does that mean? Well, basically that means we're in the megahertz. So it's anywhere from 30 to 300 megahertz. And we also use the full spectral content of each PD pulse, and you'll understand what I mean by that here in a minute, okay? I think the most important thing on this slide is the software that we utilize. Again, I mentioned it earlier. It's a proprietary TF mapping software. What that means is TF is time frequency mapping software. And why is that important? Well, as I was talking about earlier, we're measuring for RF signals. And unfortunately, there's a lot of RF signals, which we call background noise, that we don't want to look at. And when partial discharge was in its infancy, we had a lot of false positives and false negatives because we had a lot of background noise. And Techimp developed this proprietary software to actually separate the noise from the PD sources. All right, so it identifies the noise and then separates it, and that minimizes false positives and false negatives. And our software is patented. So here's a graphic of what I just explained. Basically, we'll go in and we'll place a sensor or an antenna on the cable or the asset. It will pick up those RF signals. The software actually separates the different sources, including the stuff we don't want to look at, and it will identify the type of PD, whether it be internal or tracking. And then once we identify the source and the type, we can then diagnose the problem. So we can't diagnose a problem without identifying the source and the type of PD. And the reason I say that is just because you have partial discharge doesn't mean you have a problem. It depends on the asset. Different levels of PD will affect assets differently. And what I mean by that is that, say you have 8 millivolts of partial discharge in a cable insulation. Well, that could be very, very dangerous to a cable. But 8 millivolts in a transformer or switchgear is meaningless. It's not a danger. So we have to identify the asset that partial discharge is in before we can diagnose if there's a problem yet. So different type of partial discharge. Let's talk about those real briefly. So the first one, as you can see here, is internal partial discharge, which is basically cable insulation, and it is the most harmful types of partial discharge. And then we have tracking discharge, which happens on the surface, not quite as dangerous as internal. And then corona, which is more of a spark or an air gap discharge. It's the least harmful. Doesn't mean it's not harmful. It's just the least harmful out of these three. And then we have all these graphs here in the middle, which are called phase resolved discharge patterns, and we're going to talk about these. You'll understand them, but basically this helps us identify the types of PD, whether they're internal, surface, or corona. All right, so let's take a look at this different types of partial discharge and the damage it does. So on the upper left, you'll see this is an internal discharge. Remember I talked about those water trees back there, caused by water being diffused into the insulation. Well, once partial discharge happens, you get this carbon buildup, and eventually it will fall to ground. And then the bottom here, you see this burn mark here. Obviously, this cable was installed incorrectly, and we have surface PD. It's called surface PD. You can see that. Here we have a switch gear here that obviously has a lot of partial discharge going on. Here's a joint, a splice that has what they call interfacial discharge. It's not internal because it's actually in the splice, but it's not in the insulation. So you can see the damage it's called. It's called interfacial discharge. And then you have an elbow here. Obviously, this is some burn marks here. Again, you have tracking discharges. All right. So let's talk about the testing. Again, just to review, it's done online at system voltage. We don't apply any voltages onto the cable, any signals onto the cable. There's no switching required, no interruptions. All right. What's good about this testing, it helps our customers predict failures and help with preventing unplanned outages. And of course, that helps them prioritize the maintenance and help them control their finances. So basically tells you what needs to be addressed and what doesn't need to be addressed. Again, it's non-destructive. We don't overvoltage it as we do with offline testing. It won't activate harmless PD sites, which offline testing will do. And switching transients are avoided. And again, doesn't shorten the remaining life of the cable, and it won't blow the cable up. Okay, so the testing is very, very rapid. Because it's done online, we don't have to disconnect. The advantage of that is we can do much more testing per day than offline testing. It's very safe. We always have a question, is it safe? Yes, it is. We've been doing this for 20 years. I have never had an incident. All of our technicians have the proper PPE. I'm going to show you how the sensors are applied. They're applied with a hot stick, so it's very safe and it's complete. So what I mean by complete is, again, it's not just we're not just testing the cables. Because the cables are connected to the assets, whether it's switchgear, transformers, motors, whatever, we're able to pick up partial discharge not just from the cable, from the asset as well. Okay, that it's connected to. So the report will include not just cable, but all the assets in the cable system. Another advantage of online testing. So question is, what voltage is applicable for partial discharge testing? The answer is anything for 2.4 kilovolts or above. Anything below that, we really don't get partial discharge, or we can't measure it if it does exist. What type of insulations? Well, pretty much anything you have, paper insulated lead, EPR, and then your different variations of cross-linked polyethylene, whether it's tree retardant or high molecular weight. So pretty much anything you have, we can do, in any configuration as well. So the steps are basically this. Our technicians go in and they apply a proprietary capacitive sensor just below the termination around the shielded part of the cable. And I'm going to show you some pictures here in a minute. And then we pick up any RF signal activity, and it's relayed to our data acquisition unit. And then we download it to our laptop, and then we send it to our lab where the analysis is done. And then a report is issued, and then we send the report to you. And then usually we'll have a consultation to recommend either repair or replacement. Of course, repair would be any type of equipment, transformer, switchgear, and replacement would be more terminations or cable, because you can't really repair cable that once it's partial has a high level of partial discharge. Here's the equipment. On the left is our data acquisition unit. You can see it's quite portable. It's about a little bigger than a laptop bag or briefcase. So we don't need big trucks to come in. It's very portable. It's handheld. We just need to be at least 50 feet or less from the sensor to the data acquisition unit. And here are pictures of the sensors being placed. Again, this is the UCAP sensor, U being because it's U-shaped and it's a capacitive sensor, and it's applied with a hot stick. It is grounded. It's being applied just below the termination around the shielded part of the cable. And then we also utilize HFCTs, usually for any length of cable that exceeds 1,500 feet. We'll utilize the HFCT. And what we actually do is, I think we usually use both. We'll use the capacitive sensor first, and then we'll clamp on the HFCT around the neutral or the ground lead. Both sensors are good sensors. This one just has a little more sensitivity, a little less distance, and So we utilize the HFCT for the longer segments. And then here's some pictures of the placement, again, of the placement of the sensors. I have a lot of these pictures. We can go through them quickly if you like, but here's basically we go to A phase, then B phase, then C phase, and then we'll move to the next end of the cable. Now, sometimes we cannot get around individual phases, okay, because of the configuration, whether it's going into a switch gear and these are bundled together. We have large UCAP sensors which can go around all three phases, and we're able to pick up partial discharge with that sensor around all three phases. There's sometimes that locations won't allow their switchgear being opened for various different reasons. So if that's the case, we'll utilize a TEV antenna that clamps on, or it's actually magnetic, sticks onto the switchgear, and then we're able to pick up any partial discharge going on inside the switchgear. And then sometimes we're not able to get around the ground, or for whatever reason, the splice or the cable, we also have a different type of sensor. It's called a flexible magnetic coupler, and that goes on, again, either the splice or the cable. So they're just all really different forms of antennas, all right, picking up RF signals in the circuit. Again, more pictures. This one is a little bit different. It's a capacitive coupler, and that's more for a transformer. It's next to the bushings, connected to the bushing, and then again HFCTs right here. So you get the idea. So here's a little graphic to help you understand what we're doing here. So we'll go in. We have a PD event that's going on in this splice right here. So the technicians will come in and they'll start placing sensors. They'll start, oh, there's the PD going to ground. And so they'll come in and start placing sensors. That picture's a little misleading. We'll start at one end, okay, place a sensor. And then we will always like to get a measurement on each side of the splice. So they'll place, whether it's an HFCT or a UCAP on each side of the splice, and then pick up those RF signals, and then they'll send that information to the lab. Now this graphic is exactly the same thing I just talked about, only it's in a pad mount utility type situation. Same thing though, we just below the termination, you put the sensor. If there's a splice here, we'll do it on each side of the splice, and then we'll move to the next test point. All right, so let's talk about data analysis for a moment. Again, I mentioned we measure both frequency and time domains, and we employ the TF map. Again, why do we have TF mapping? It's basically for noise rejection for all those RF signals that we don't want to look at. So we separate the sources, including the noise, and then we can identify the stuff that we want to look at and help identify if there's danger inside that asset. Okay, and then we identify the defects using the phase resolved discharge pattern. I'm going to show you what that is. It's basically the signature of the type of PD. All right, so first thing you want to remember with this is that with all RF signals, as we move away from the source of partial discharge, amplitude and frequency are going to decrease. All right, just like any RF signal. So as we move away from the PD source, amplitude and frequency will decrease. Why is that important? Well, it helps us identify the location. So let's say we come in and we have a T-body with a partial discharge happening. That's where the little yellow dot is. And we take a reading 60 feet away. This is what we would see. Okay, we'd see 25 millivolts of amplitude, and we have a frequency range going anywhere from, what is that, about 15 to 175 megahertz. And then we move that sensor away and take a reading. Amplitude drops 16, and as you can see, the bandwidth has dropped. And then we go to 600 feet, Again, amplitude has dropped to 8, and you see the frequency bandwidth has dropped a lot. So what that tells us is we're moving away from the defect, or the data. The person analyzing it says, hey, wait a minute, we got the partial discharge, and this is where it's at. All right? Now, what he doesn't know at this time, because he doesn't see the little yellow dot on the T-body, he doesn't know what asset that partial discharge is in. He doesn't know if it's the T-body, he doesn't know if it's the cable, he doesn't know if it's the asset to whatever this T-body is associated with. So the next step after location is to identify the asset, all right, or identify the type of discharge. So that's where the phase resolved discharge pattern comes in. All right, those are those. Remember when we started, we saw those the graphs and the dots like this, and this is what's going to tell us what types of PD we have, partial discharge. Okay, so the first two, signal intensity, which is amplitude, and pulse repetition, which is how many times it's happening per cycle, will determine if it's dangerous to that asset. Okay. And then the phase angle, where it's happening in the cycle, the signature, which is this pattern here, which every little dot represents a partial discharge, and they develop patterns, as you can see. And being synced to the circuit will help us identify the type of discharge. So remember I said we acquire the complete PD pulse. This is why, because we're measuring time and frequency. Time being the time length of the pulse, all right, how long that pulse is happening, and then the frequency, all right? So why is that important? Because of this, basically. This pattern is a pattern, a discharge pattern. It's from a variable frequency drive. So what we have a lot of dots with a lot of different colors, okay? And in there is a lot of background noise from the variable frequency drive, along with some other sources of PD that are coming from the assets. So what the TF mapping software does is it takes all these little dots and it puts them in clusters. It maps them, okay, in time and frequency, and we get these clusters, okay? And once we get these clusters, so all these dots have been moved over here. Okay, and once we get these clusters, then we are able to identify what the background noise is, and we can get rid of that, and what the PD sources that we want to look at are. So this red cluster is internal PD, and you can see once we take that cluster and we map it to the circuit, we get a PD pattern. All right. So this is internal PD, if you remember, the most dangerous PD there is. And the blues, we're going to take that and do the same thing. Boom. And we've got a pattern, and we've got, the analyst will know by this that it's surface PD coming from the T-body, could be coming from a bus bar. Of course, internal would be coming from the cable. So now we've got location, and now we've got the asset. All right, easy stuff, right, guys? All right, so let's just take a look at the three patterns. This is a typical PD pattern for Corona, which is a air gap discharge. All right, and then once we know that, we'll take a look at the amplitude and how many times it's happening per cycle, and then we know if it's dangerous to that asset. Here's the phase resolve pattern for surface discharge. All right, obviously that looks a lot different than that. And then we'll take a look at amplitude, repetition rate, and then we'll determine if it's dangerous to that splice or bus bar or termination or whatever. And this is the damage that surface PD does to your cable or splice or bus bar. And then finally, the bad boy is internal discharge, of course, for the cable, the most dangerous. This is what it looks like, and this is what the damage has done. These are the water trees I talked about earlier. that are caused by water diffused into the insulation. And then eventually PD will happen, partial discharge will happen, causing this. And then if we pick it up early enough, we can determine if it's dangerous or not dangerous. And if it's dangerous, then obviously you want to replace it before it fails. Again, amplitude, repetition rate will determine the danger level of that PD. And basically all this, what we do is basically give you a probability of failure, which allows you to replace or repair that asset before it fails. So what causes partial discharge? Well, all of this, I won't go through all of it, but we talked about contamination. We talked about treeing, protrusion, interfacial discharge. This is what a little graphic of what water trees look like. And then once PD happens, what they look like. And of course, once this happens, it'll fall to the ground.